Well, welcome everybody to this edition of Gauge Theory Virtual. And we have David Duncan here really this week, and he is going to talk about gluing mASD connections on cylindrical ends. I'll let him take it away.
All right. So I just passed to full screen. I trust you can still see that. Oh, geez. I guess it's going to go ahead and do it on its own. All right, so I'll scroll. So here we go. So this is joint work with Ian Hamilton, who I think I saw in the audience just a minute ago. Oh man, it seems like Zoom is interacting strangely with this. Let me see if I can. Are you guys able to see?
Yes.
All right, here we go.
Yeah, it looks fun.
Okay. So here's the setup. We've got X is going to be a connected oriented 4-manifold with cylindrical ends. And for me, N is going to be the 3-manifold, sort of the one down at infinity. Equivalently, you could think of it as being the, well, any cylindrical end 4-manifold can be written as a compact piece together with an end, and N could be thought of as the boundary of this compact piece. So E for me is going to be a G bundle over X. And then as a reminder, so I think probably everybody in the crowd knows this term, connections ASD if the self-dual part of the curvature is 0. And so the general goal is to study the moduli space of ASD connections. And so that's ASD connections modulo gauge transformation. And so let's just take G equal to SU2 to make some statements a little bit later. Just be a little bit easier for me to put down. So there's a difficulty in the cylindrical end setting. And that's the moduli space is not cut out by Fredholm equations, at least in general. So here's a little cartoon where maybe you have sort of poor stability conditions in the absence of Fredholm conditions. So maybe you have some sort of singularities in the moduli space. And if you tried to perturb, then, well, it's not exactly sure what's happening as you do the perturbation scheme. One way of understanding this lack of being cut out by Fredholm equations is by paying attention to what happens to ASD connections down at infinity, and so you can, I guess the finite energy ASD connections, I guess, is really what I should be looking at here. The ones of finite L2 norm, those are all asymptotic to flat connections, and in some sense the poor behavior of the moduli space in general comes from degeneracy of those flat connections, and you could think of that degeneracy as being maybe in the Moore spot case, in the Moore spot sense. So Fleur had a fix for this, and his fix was to perturb the equations. And so in this little cartoon, we had this sort of singular point here, and his perturbation resolves that singularity. But how does that work a little more concretely? He took the ASD equation and then modified the right-hand side by some sort of alternative extra function, and showed that he can choose that function well to obtain Fredholm equations and things like that. And now the catch here, though, for Fleur at least, is that the types of functions that he's perturbing with, they'll destroy the behavior down at infinity, and they necessarily are going to screw around with the flat connections. And so that's good for a lot of purposes, like if you're doing Fleur theory. But if you, for example, know something about the moduli space of flat connections, the representation variety, say, maybe you don't want to destroy that representation variety. Maybe you don't want to perturb that away, and maybe you want to preserve that, for example. And so maybe you want to work with ASD equations on the nose, not some sort of perturbed version. And so the solution by Danny and some of his co-authors in '94 was to thicken the moduli space. And so what does that look like? Instead of perturbing the moduli space of ASD connections, you stick it inside of a bigger space that is cut out by Fredholm equations. And so it's this bigger space that I want to talk about today and tell you a little bit about. So here's the picture from the previous slide. What do their equations look like, the Morgan Mrowka Ruberman equations? So start off with this, this ASD equation, and then they add this extra term here. And so what are the components in this extra term? Well, if my cylindrical end 4-manifold is pictured down here, here's the cylindrical end, this beta is a cutoff function that's supported on the end here. Now this J thing, that's the interesting part. They spend about a third of a book or so, maybe a little more than that, constructing this J thing. But ultimately, the key features for me is that this J factors through a finite dimensional manifold. And I guess the important geometric property is that it parameterizes the connections that are relevant for the conversation. It parameterizes them by their asymptotic behavior. And so they're able to show that sort of this, with their very interestingly and very nicely defined function J, that they do in fact get, I guess, a nice set of equations in the sense that the set of equations are Fredholm. One other key property of this J thing is that if A is ASD and also sufficiently close to some reference connection, and I'll bring that up again a little bit later, then this extra term they add is automatically 0. And so it's due to this second bullet point that the moduli space of ASD connections is sort of a subset in some sense, and I'll spend more time talking about this, is sort of a subset of this thickened space. So, so this is effectively what I just said in the previous slide. The map that sends A to this sort of modified version of the ASD operator is Fredholm, at least, well, I have some caveats here I'll tell you about in just a minute. And then it also maps ASD connections to 0. The first caveat is that it's Fredholm as long as you restrict to a certain slice, and as long as you do the usual things of having a good Sobolev norm on the domain and codomain. And then the second caveat here is that it maps ASD connections that are sufficiently close to a reference connection. So same caveat as before. So then you define a connection to be modified ASD or mASD if it's lies in the 0 set of this operator. And so then I want to consider the space of modified ASD connections and then restrict to a Coulomb slice. So that way I can have a Fredholm setting. So the little hat for me is going to denote this modified version. So then you say the connection is mASD or modified ASD if it's 0 set. This is just I've repeated from the previous slide the relevant things for this slide. And so this whole construction here depends on various choices. So I want to tell you a little bit about those. So first you need to fix a flat connection gamma on the 3 manifold N. And in some sense, this is just saying we're going to be interested in those connections that are asymptotic to gamma or something sort of close to gamma. And the details of that I don't really want to get into, but that has to do with that little J function from the previous slide. But that information of gamma needs to be specified. You also need to specify a connection relative to which you're going to define the slice. And so I'll talk more about that over time, but that choice needs to be made. And then there's a bunch of other stuff, like cutoff functions is one thing that shows up. This beta is you make that choice. And then there are a lot of other choices that are involved in the construction of this J. So all that other stuff we'll call thickening data, and we just abbreviate it by a calligraphic T and not talk about it again, at least not today. So when the choices are relevant, I'll decorate this M hat space by the appropriate choices that are relevant for the moment. So then the main result, or one of the main early results of the book by Morgan Mrowka Ruberman is that these modified spaces cover the ASD moduli space in a certain sense. And so here's a little cartoon to illustrate what that sense is, or at least how I think about this. Imagine this is your mASD moduli space. Imagine this is your ASD moduli space. This is the thing that is not necessarily cut out by Fredholm equations, but we want to put it inside of something that is a little bit better behaved. So here it's these little dotted lines you could think of as being, like the stuff you'd want to compactify with. For example, maybe this one here is reflecting things like energy energy concentration. So like bubbling maybe is happening here. Maybe there's energy loss down the cylindrical end, and maybe that's what that boundary component is capturing. And then in here, maybe there's some sort of interesting behavior on the interior, and so I'm indicating that by these little arcs that sort of pop out of the otherwise nicely behaved space. So let's say that we wanted to cover this point right here, this ASD connection represented by that orange dot. So so there's going to be some little neighborhood in the ASD moduli space, and there's going to be some collection of this extra data, so that there's an embedding from this little neighborhood in the ASD moduli space into this, what they call the thickened space, the mASD space. And so you can play the game with every single point in the ASD moduli space. For example, you can pick a point over here, and then there's a little neighborhood. And maybe it's the case that everything in the mASD moduli space is actually ASD. That's sort of what's indicated in this picture. Whereas in the first orange picture, there's this white stuff that's properly mASD, whereas only the orange stuff is ASD. Or maybe you've got this point down here, right where this little arc hits the plane. So it'll have a little neighborhood, and the neighborhood in this ASD moduli space will have a little bit of that arc plus a little bit of the plane. And then the associated thickened part will have to somehow capture all of that in some nice way. And so maybe in this case, it'll be a cube. So the mASD moduli spaces may jump in dimension, for example, as you dive around from point to point. But the result is that you can cover the entire ASD moduli space with these things. So previously, the goal was to study the ASD connections. And the updated goal is to try to do for the mASD connections, this M hat space, what has been done for the ASD connections, the M space. And so what are the differences? So the first major difference is that this M hat thing is a local object in the sense that I was talking about on the previous slide. You should really think of it as being something like a cover of the ASD moduli space. So that is particularly important when you do things like compactness, which I'm not going to talk much about today, but that would become really important there. Another important difference is the operator for the mASD space. This is generally not gauge invariant or gauge equivariant. And you can see that in this J function. I mentioned on a previous slide that J factors through a finite dimensional manifold. And so there's going to be no way that this term here is equivariant in the same sense that this one is. And in fact, it turns out this is gauge invariant, while this one is equivariant. It turns gauge action on the A variable into the adjoint of the values of the gauge transformation on the curvature, the two-form part. So then what's the same? And that's what I want to tell you about, which is gluing. So you can do gluing in this mASD world. Oops. So here's our one way to phrase one of our theorems, and it's I guess the mASD version of what you are used to in the ASD world. If you've got B2 plus equals 0, then there's an mASD connection on your bundle, and that is irreducible and regular. Regular meaning that the appropriate linearized operator is surjective at that point. Not only that, but you can have it to have the right second Chern class. And this gets a little, this conversation is a little bit different in the mASD world than it is in the ASD world. And the difference is that in the ASD world, the energy of an ASD connection is a topological quantity. It's effectively the second Chern class. Whereas in the mASD world, that's no longer a topological quantity. And the energy, so to speak, you have to be a little careful as to what that even means. But the right thing to look at is the relative second Chern class here. And you can think of that as being the Chern-Simons value of the flat connection at the very, very end. And so in this whole conversation, the mASD connections in general won't converge to a flat connection, but they'll converge to a connection that's pretty close in the representation variety to the flat connection gamma that you've fixed. And so then you can make sure that the Chern-Simons value of that asymptotic connection is as close to, let's say, 1 as you want. If your mASD connection happened to be ASD, then the relative second Chern class would actually equal the second Chern class, and it would be equal to 1 on the nose. So then corollary, let's suppose that 3 manifold down at the end is a circle bundle over a surface that has positive Euler class. Then the mASD connection from this previous theorem actually is ASD. And so you can view it as an existence theorem for ASD connections. And so it's a special case of this corollary. Consider the case where the compact part X naught is diffeomorphic to the total space of a disk bundle over a surface with positive Euler class. Then the corollary tells you that there's a finite energy. I didn't say this here, but it'll be irreducible and regular ASD connection on on X. And not only that, but this is the case for any metric that decays on the end to a cylindrical metric. So first I'll talk about the proofs of these things, and I'll start with the corollary. So here's the data from previous slides that I think are important here. The observation is ultimately won by Morgan Mrowka Ruberman, that this J thing is automatically ASD no matter what A you put in there in the setting of this three manifold. And so, well, if J of A is ASD for every single relevant connection A, in particular, J of A will be ASD for that mASD connection guaranteed by the previous theorem. So this part will automatically be 0. Well, that means that FA plus is equal to 0 for that mASD connection. So your mASD connection is actually ASD. Moving on to the main theorem, like I guess the first of the main theorem. We'll have another one later. How's the proof go? You glue, right? So what does gluing look like? You pick your favorite point. So here, this flask-looking thing is my X. There's the end, and I don't want to glue down the end. I mentioned earlier that there's this cutoff function beta, and it's supported, let's say, on the right to the right of this dotted line here. So I want to make sure that the gluing is taking place on this compact piece. But you pick your favorite point in the compact piece, pick your favorite point in the force sphere, and then you carry through the usual gluing procedure. And not much of it is really, or most of it carries over as expected. And when I say carries over, I mean the gluing construction from the ASD world carries over to this mASD world without too much of a problem. I mean, in some sense, the equation was designed so that it would, though I don't necessarily think they had exactly this application in mind, but they set it up so it'd be Fredholm. The major difference is just how do you contend with this extra piece here. And the way you do that is, again, you use the observation that J factors through a finite dimensional manifold. And so then the finite dimensionality of that manifold gives you all the relevant estimates you need here. There's one other catch that's different between this mASD version and the ASD version, and that's that we're working entirely in a Coulomb slice as opposed to working modulo gauge. And that's well, you can't work modulo gauge because this equation is not gauge invariant, so you have to do something like work in a slice. So there are a few times in the proof, a few places in the proof for the ASD version of gluing where you just say, because we're working modulo gauge, you can, ignore this little feature. And so here I can't do that. I have to actually see how it looks within the specific gauge slice, but that's not a major hurdle. So I want to give a little bit more details about, I guess, how this gluing procedure looks, and then also how it differs from the ASD world. So ultimately, it comes down to an implicit function theorem argument, and for that you want to linearize the defining equations, and for us it'll be at the trivial connection in this context of this gluing in a bubble. And then you want the linearization to be Fredholm and surjective, as I sort of said several times. So how does that look, and why can't it be done purely in the ASD setting? So the linearization of the ASD operator is the Durham operator coupled with your Lie algebra, and then you take a self-dual part of it. Now, you want to be working in a context in which you can use an implicit function theorem, so extend a Sobolev completions, and do the ones whose first derivative are in L2, mapping into L2, for example, would get you started at least. So this operator will take in a 1 form and spit out a self-dual 2 form. So this is just for the previous slide here. Now, Lockhart-McGowan type theory says that when H1 of n is not 0, this thing's not Fredholm. And there's a little asterisk that I'll talk about in just a minute. But if you put a little weight on it, if you weight by delta, have some sort of exponential weights, then you do get a Fredholm operator. And when I say Fredholm here, I mean we should actually be working within a slice. So couple this with the Coulomb gauge operator as well. So that's the caveat. Okay, so we want to be working in these delta decaying spaces. And what's the choice on delta? Well, if you just are interested in the Fredholm operator, you could pick any delta that's outside of the spectrum of the flat connection of the Laplacian of the flat connection down at infinity. So most delta. For our purposes in the gluing, we're going to want to do delta that are positive, but just lower than the first eigenvalue of that Laplacian I just mentioned. So again, I'm trying to make an argument at the moment as to why you can't necessarily carry out gluing in the ASD world, but you need to do this sort of thickened modified version. And so one way of phrasing this is by a long exact sequence that's pointed out by Morgan Mrowka Ruberman in their book. And it looks like this in the context that's relevant here. So H1 of n is, what that is. Then you got the co-kernel of this D plus operator. That's the thing that you would need to, you'd need that co-kernel to be 0 here in order to be able to do gluing. And then there's this H2 of E delta. Ultimately, we'll see that, maybe I'll just tell you, we won't see it. I'm just going to tell you that this E delta is the complex associated with the modified ASD operator. And then the key feature at the moment, though, is that the dimension of H2 is B plus of X. And so, as I just said, this H2 delta, that represents the kernel of the mASD operator. And so then what you see is that if H1 is not 0, that is, if you're in the setting where the Durham operator is on one forms, well, if H1 is not 0, you guys can phrase all the equivalent versions as you want to that. But if you do know that B plus equals 0, so that is, if you're in a setting that's where the Morgan Mrowka Ruberman stuff is interesting, which is when H1 is not 0, but when, for the purposes of this current conversation, B plus is 0, that means that's 0. Well, what that's going to mean is that this co-kernel of D plus is not 0. And so ASD connections alone are not going to be enough to get around the obstruction. On the other hand, this is the obstruction here for mASD connections. And when B2 plus equals 0, that obstruction vanishes. And so actually, I think I saw Chris Gaduda here, and I'd like to thank him for asking me a question about this a couple of weeks ago and got me thinking about it. So Chris, I think this answers the question you asked, but you can tell me at some point later if you still are unsure. So the next thing I want to talk about is extending this whole conversation to families. And that's the type of thing you do with ASD connections, and can you do this in the mASD world? And this is where I think things get a little more interesting, both from a geometric setting and from an analytic perspective. So on a previous slide, I talked about gluing. You pick your favorite point in the compact piece, and it'd be nice to be able to allow that point to vary, for example, and sweep out some, maybe ideally an open subset of the mASD moduli space. And so that would do something like give a partial compactification, and that would be the hope, and ultimately we're able to do that. So I want to tell you about how that works. So the difficulty is that as you move the point around, say, if you trace through the proof that I didn't tell you much about, the Coulomb slice moves around also. And so that means that your moduli space, or this thickened space, probably shouldn't call it a moduli space because it's I've intersected rather than quotiented here. But this thickened space, it's going to move around as you move that point. And so you say, oh, well, there's no problem. If you move from one Coulomb slice to a nearby one, you could always use a gauge transformation to put you back, in your favorite Coulomb slice. But the catch is that the mASD connections are not gauge invariant. So, or the space of mASD connections are not gauge invariant. So you could find your gauge transformation that'll take you from your new Coulomb slice to the one you want it to be in, but that'll destroy the mASD condition. And so that's one of the major obstacles in I guess extending this. And so then the resolution is, well, we'll use the implicit function theorem again. Well, you can find a Coulomb. You can find a gauge transformation that'll take you from the slice you found yourself into the one that you want to be in. As I mentioned, you've destroyed the mASD condition, but you're still going to be close to mASD. And so then use the implicit function theorem again while staying in the slice you want to be in. And so I'll state a theorem to that effect in just a minute. I think I was thinking about how to put this together, and I think the easier way, the way that I feel most comfortable stating this is if I extend the conversation to not just gluing in, let's say, an ASD connection on a copy of S4 that you've connected summed on there, but let's just do the connected sum of two different four manifolds. So let's extend the scope. So now my X is, here was the X I had previously, and now I'm not necessarily just putting in a four manifold, but maybe some other, or sorry, not necessarily just plugging in the four sphere, but maybe some other cylindrical end four manifold that I'll call X2. So in that setting, you want to be able to have families of mASD connections and glue them together, and hopefully that'll produce a family of mASD connections in the glued four manifold. And so pick pre-compact open sets, G1 and G2, in the space of mASD connections. Now A1 prime here, that's specifying the Coulomb slice for this one. A2 prime is specifying the Coulomb slice for this one. G2 means everything here is going on X2. G1 and A1 means everything is going on X1. Reg means regular. So these are the relevant linearized operators should be surjective at all points in here. And so then you can do something in the, that I think probably many of you know about, but you pre-glue, which means you just stick them together using a cutoff function to give you a connection defined on X. And it'll be close to mASD, but not exactly mASD because your cutoff function is, well, who knows what it's doing. And so then, like what happened in in a previous slide, you can then use the implicit function theorem to take your almost mASD connection and make it into an actual mASD connection. So you've done the actual gluing, solving of the implicit function theorem type gluing. And so I'll call that J of A1, A2. And it's, you can do that in such a way that it's, this thing belongs to this A prime slice. And so then ideally you want to view J as a function from.
Hey, David.
Yeah.
I don't know whether whose end it was on, but my audio cut out for like a minute there. Could you just go back to somewhere where it was sort of in the middle of that slide, just before the just before what you said now?
Yeah, for sure.
Thanks.
Yeah, so so we're fixing G1, which is a pre-compact open set in this mASD space of connections. Reg means that I want all my elements of this to be regular. Meaning the relevant surjective operator is, sorry, the relevant linearized operator is surjective. And then A1 prime, that's specifying a Coulomb slice. And so the subscripts of 1 means that all of this is taking place on X1. And then there's a similar thing taking place on X2. Now you've got a connection A1 prime and A2 prime on each of the two pieces, X1 and X2. And so you could pre-glue them. And what that means is you take a cutoff function and you just meld them together, in some sense arbitrarily, to make a connection defined on all of X. And these ones, A1 prime and A2 prime, they were mASD. This pre-glued connection will no longer be mASD on the nose, but it'll be approximately an mASD connection. And then you can use the implicit function theorem type argument from before to actually pass to an mASD connection on the nose. So pass from the approximate mASD connection to an actual mASD connection. And that'll be regular as well. And you can do that in such a way that all this is taking place in the Coulomb slice associated with this A prime. So just by doing the implicit function theorem that I talked about earlier, just doing it one piece at a time, A1, A2, as A1 and A2 vary over G1 and G2, you get a function from G1 cross G2 into, well, you'd like it to be into a fixed mASD moduli space. But the problem is that as A1 and A2 vary, this A prime varies. Because, well, A prime depends on A1 and A2. And so And so as A1 and A2 vary, the moduli space that, or the thickened space to which it belongs is going to vary as well. So we won't be able to get J as a function into a fixed mASD space. So instead, to, I guess, rectify that, we'll turn J into a section of a bundle. I mean, that's the usual thing. If the spaces, if the codomains are varying, then just throw those things together and do a bundle and consider sections of that instead of functions. So that's what we're going to do here. So from the previous slide, you've got an mASD connection that you've glued together from mASD connections A1 and A2 on the different pieces of X. And then what's the ostensible bundle? It's going to turn out that this might not actually be a bundle on the nose, but it'll be close. So we're going to pair them up. A1 and A2 are the points in your parameterizing spaces of mASD connections on the pieces. And then this third component, A, it's going to be just any element of the mASD moduli space that belongs to the slice associated with your A1 and A2. So then you get a projection to the first two components, just project downwards. And so the fibers are going to be exactly, the fiber over A1, A2 is going to be this space here. Then you can make a section. So before we had this J, which is, I wanted to be a function, but well, I wasn't going to cut it. So we piece it together as the third component of a section, calling the section psi. And so, I mean, this part here clearly belongs to the Coulomb slice defined relative to itself. So this isn't a very deep definition here. It's just designed so that that this whole thing makes sense. And so then the theorem is going to have two parts. The first part is that this E thing does give us a bundle. Well, sort of. There's a neighborhood in E of the image of psi, so that if you restrict to that neighborhood, then that restriction is a locally trivial fiber bundle. I'll draw a picture of this in the next slide. And then the fiber is going to be an open subset of the space of regular connections relative to some reference connection. And that doesn't really matter what this is. It's just, yeah. And so then the next part is in some sense the thing that I'm after. And it's that for every point in G1 cross G2, and G1 cross G2, that's my parameterizing space. That's the mASD connections on the first piece. G2 is the mASD connections on the second piece. So every point in here has a little neighborhood, I'll call calligraphic V. And then there's a smooth map from this V into this fixed mASD space. And this map phi is a diffeomorphism onto its image. And so what that's saying is that as you move around in G1 cross G2, you really are pushing out a full open set in the mASD moduli space, or mASD space. And so that's the type of result that you'd expect from the ASD world, where as you vary, like in the ASD world, you've got ASD connection on one piece, ASD connection on another. You can glue them together to get an ASD connection on the connected sum. And then as you vary A1 and A2 in its moduli space, and each of their moduli spaces, you sweep out an open subset of the moduli space on the connected sum. And so this part B here is really the result that we want. And maybe said differently, it's saying that at least in the image of this phi here, every single connection can be every single mASD connection is approximately 1 on X1 and approximately an mASD connection on X2, where you think of X1 and X2 as, well, yeah, before you took their connected sums. So here's a verbatim version of part A from the previous slide, and I want to draw you a little picture of that. So we've got this E space, which I don't really know what it looks like pretty far away, but we got this E space, and jagged means could be messy. I'm not really sure. We had G1 and G2 down here. Pi was a projection from this E space down to G1, G2, and then psi was a section. So what I've drawn here is the image of psi is all this here. And so then the point of the theorem was that the image of psi has a little neighborhood where that if you restrict to that little neighborhood, then you actually get a locally trivial fiber bundle. It's not making any claim about what's going on in this jagged bit there. So then, let's see here. Actually, I'm noticing I talked faster than I was expecting. But so then part B, how does that look? For every point in G1 cross G2, there's a neighborhood and a smooth map that's a diffeomorphism onto its image. So here's how I picture this thing. So this little square right here, well, maybe I should say this. G1, G2 is on the bottom. We've got some little neighborhood V inside G1, G2. And so in the previous slide, it's like V lives right down here. And then take the pre-image of V upstairs and then intersect that with U. So these dotted lines here are the same as these dotted lines here. So I'm intersecting into the U, which is the thing I know is a locally trivial fiber bundle. So since up here I'm in a locally trivial fiber bundle, I can pick a local trivialization. And so it's going to be of the form, well, V is going to be this direction. And then the fibers are all going to be some open subset. Yeah, technically this should be some open subset in the mASD space for this reference connection. And so each of these fibers then belongs to the same space. And so this map down here is a projection to, I guess, this component to the x-axis, whereas the map to the right is a projection to the y-axis. And so if you follow this, this black line through, the image of psi is the black line that's arced on the left. And then it turns into something on the middle picture. And as it turns out, it turns into something like this diagonal line. And then when you project it, it goes to something over here, this straight line. And ultimately, it turns out that this projection is one-to-one. So that's part of what's going on in this theorem. And so the map phi from this theorem goes from down below here straight up here, and that's the diffeomorphism of the theorem. So yeah, so there we go. I went a lot faster than I thought I would. I apologize about that, but I think that at this time of year, people aren't too offended if people go a little bit early on seminar talks. But thank you.
Thank you, David. We certainly have time for questions. I'll ask one. Do you and Ian have application in mind?
Yeah. So ultimately, I mean, maybe Ian will take over here in a minute answering that question, but it would be nice. Let me see here. There are a lot of settings where you'd want to be able to do, say, ASD type, moduli space stuff, but relative to not necessarily a generic metric, like maybe relative to a metric that is invariant under a finite group action or something like that. Or it'd be nice to, so Ian has several examples like that in mind, and that's what I'm gonna probably appeal to him to tell you about, because he knows more about that than I do. But there are some heuristics that say that if you can carry over, for example, gluing, for example, compactness and things like that from the ASD world over into the mASD world, then you can, for example, recreate some of the sort of like the Donaldson type arguments where you come up with a cobordism between the four manifold that you started with and, well, who knows what it'd be in the mASD world, but something like a connect sum of CP2 bars. So like that type of argument would be the type of thing we'd like to be able to do. And we'd like to be able to do that without perturbing what's going on down the cylindrical end. So I'm not sure if Ian wants to take over and talk about the specific applications beyond that. So I'll open it up to him if he wants.
Well, just to add that the idea of using the Morgan Mrowka Ruberman moduli spaces to study group actions on smooth four manifolds is a long dream of mine. So far, hasn't led to any concrete results. But this project with David is part of an effort to start to do the foundational parts of the MMR theory without, as David mentioned, without assuming a generic metric, which is exactly what you don't have if you have a smooth four manifold and a finite group acting on it, and you need to work with a metric which is invariant under that finite group action, and these are essentially not generic. And all of the usual tools of smooth topology, like transversality, just don't work equivariantly. So there's a different kind of theory when you try to work with a fully equivariant version of the Yang-Mills type moduli spaces. So this is like a step in some direction, which we've been hoping for.
So maybe just if you could just elaborate a little further. I mean, those issues that you mentioned of equivariant transversality, that's present even in the closed case, and the sort of mASD business is, as David explained so nicely at the beginning, have a lot more to do with singularities of the sort of restriction map to the representations on the end. So how does this help you sort of deal with that the sort of failures of equivariant transversality?
Well, I mean, one part of your question might be how does cylindrical end manifolds help you to deal with any of the equivariant issues? And that, okay, I guess one answer to that is that the even simple questions about if finite groups acting on even a cyclic group acting smoothly on a four manifold, when you have an isolated fixed point, then you have these local representations of the group. And so these are, in determining the structure of those representations, there's a relation given by a T-Singer index formula, but determining exactly what they are depending on the topology of the four manifold is a challenging sort of problem in general, just not understood at all. So one idea to try to deal with things like that is to work with cylindrical end four manifolds where you attach tubes around neighborhoods of these isolated fixed points, and then the cylindrical end theory appears to have certain possible advantages in dealing with the moduli spaces that arise.
Oh, yeah, thanks. So maybe this would be then to David, I mean, I know this is all at the beginning, but is there some at least conjectural picture if you were gluing things with in the standard case, if you're gluing things where B2 plus is positive, there's a kind of a picture that we got from Taubes and Donaldson of obstruction bundles and stuff like that. So does that all show up in a similar way here, or is that what you expect?
Yeah, it shows up pretty much exactly as you'd expect, and so our paper works it out in that general setting of obstruction bundles, and and so we can use the same framework, for example, to get an existence result for B2 plus equal to 1, say. We didn't work it out for higher B2 plus than 1 just because it was already complicated enough. The extra terms in the mASD operator, they do start to add up. And if you look at Taubes's paper on, for example, existence of ASD connections when B2 plus is larger than 1, actually, that's already pretty, there's a lot going on there. So we figured the paper was already long enough. So we just did existence for B2 plus equals 0 and 1. Yeah, so that works out sort of as expected. The I think the hard part, it really is compactness. And there's all sorts of ways in which a sequence of mASD connections can escape off to the boundary, say. And some of those are built into the mASD equation to begin with. Like I mentioned, it's an inherently local object. And so you would say things like, well, what happens if various points get close to the boundary of where your cutoff function is supported, things like that. But there are sort of more geometrically interesting ones as well. Like suppose you've got a sequence of mASD equation of connections, and you've got energy that's escaping down the end, like the typical picture that you see in the ASD world. And even if none of the other strange things are happening, but if you just have that has become a standard picture, it's also not really clear what's going on with the mASD. It's not really clear what the limit is going to look like. For example, one of the main issues here is because the energy of the mASD connections, whatever that means, but it's not a topological condition. So you don't have a topological constraint saying, you don't have an a priori topological constraint giving you bounds on like the number of trajectories that are breaking off in such a limit. And so as far as I can tell, it's conceivable that you could have an infinite number of trajectories breaking off in such a limit. And we don't yet have a way to rule that out. And so that's like the next thing that I'd like to dive into, because I think it's pretty interesting. But that's definitely, I think, one of the challenges we're gonna have to figure out in the next stages of this project. And that may be another challenge. I mentioned that this gluing that we do takes place in the compact part. I don't know how to do gluing like this if you try to glue on the end itself. There's a lot of interactions that take place between the gluing and the mASD equation. So like on the end, I guess in the compact part, the mASD equation just literally is the ASD equation. So that's one of the major features why a lot of the old techniques carry over to the new setting. But if you try to glue literally on the end, on the cylindrical end, where the mASD part of the mASD equation is non-trivial, then that becomes pretty complicated. And so we didn't work that out in the paper because a lot of the applications we have in mind don't need that. But that would be another thing that would be worth diving into at some point.
Yeah, well, that was a lovely talk. Thank you, David. People are being shy with questions.
Okay.
As you say, it's the end of the term and people can get tired, especially if they don't have a spring break. We will certainly reconvene next week with Josh Wang. So I wish you all a lovely week.
Well, thanks for coming, everybody.
Okay. Thanks, David.
David. Thank you.